You know that feeling when you're talking to an AI chatbot? It's like you're chatting with a brilliant parrot that has a terrible memory. It can write a beautiful poem or a perfect chunk of code, but ask it what you talked about 5 minutes ago and nothing. It's a total blank slate. Okay, so today we're going to dive into a pretty radical proposal that wants to fix that, to move AI from just predicting words to actually thinking. It's called Spin-Resonant Geometric Intelligence.
And this quote from the proposal's author, Joseph Defendre, it cuts right to the chase, doesn't it? The massive large language models that we all use, the ones built on the transformer architecture, they're basically just the world's most sophisticated autocomplete. I mean, they're incredible at spotting patterns in data, but they don't understand what they're saying in the way that you and I do.
And that leads us to the big one. This is the multi-billion-dollar question that the entire field of AI is wrestling with right now. If just predicting the next word has its limits, if it's not going to get us to true intelligence, then what's the alternative? How do we actually build a system that can hold a coherent, continuous stream of thought? So before we can even start to build a better mind, we've got to figure out what's wrong with the ones we have now. Let's really dig into where today's AI is falling short. This table here lays it all out pretty clearly. When an AI forgets your name in the middle of a conversation, that's the no persistent memory problem. And when it confidently just makes things up, what we call hallucinations, that's a huge poor reasoning issue. And look, these aren't just weird little quirks. They are symptoms of a system that thinks one single token at a time. It has no continuous thought process, no stable idea of itself to keep it grounded. The SRGI model we're talking about has specific fixes for each of these, things like attractor memory and resonant dynamics. And trust me, we're going to break down what those mean.
Okay, so if the current digital approach is kind of hitting a wall, where do we even look for inspiration? Well, this proposal suggests we look at the two most complex, most successful information processors we know of, the entire universe, and of course, the human brain.
It's pretty fascinating when you think about it. On one side, you've got physics, which tells us that on a deep, fundamental level, reality is built on geometry and resonance. You know, things vibrating in very specific, stable ways. And then on the other side, you've got neuroscience, which is showing us that our brains aren't just giant calculators doing matrix math like a computer. Nope. They are these incredibly dynamic networks of neurons that are oscillating, they're synchronizing in these complex geometric patterns. Two totally different scales, but they share a common theme. Let's start with the physics side of things. Einstein showed us that the fabric of reality itself has a geometric shape. Quantum theory tells us that particles, the very building blocks of matter, are really just stable vibrations, or resonances. So the big takeaway here is that nature uses geometry and resonance to build things that last, things that are stable. So, why shouldn't an artificial mind be built the same way?
And guess what? We see those exact same principles right inside our own heads. When you're holding a thought in your working memory, it's not sitting still. It's actually groups of your neurons firing together in a synchronized rhythm, a resonance. That's literally what keeps a thought alive. And our long-term memories? They're stored in what neuroscientists call attractor networks. These are stable patterns that our brain can kind of fall into and recognize. So we're not just crunching ones and zeros. We are creating these beautiful, resonant geometric patterns.
All right, so we've looked at the problem, and we've seen where the inspiration is coming from. Now let's get into the heart of the solution that's being proposed. This new architecture called Spin-Resonant Geometric Intelligence, or SRGI for short. The first really big idea here is to completely change how an AI even represents a word. Right now, a word is just a point on a map. SRGI says no, let's use something called spinor embeddings. Now think of it like this. Instead of just a coordinate, every single concept gets a compass needle that points in a specific direction, and it gets a rhythm, or a phase. So why is that important? Well, the direction keeps track of how it relates to everything else, and the rhythm tracks how that relationship changes over time. That's how you build real context that doesn't just evaporate.
Next up, you've got these resonant layers. So if the spinor embeddings give our thoughts a rhythm, these layers basically act like tuning forks. They're built specifically to vibrate with, to amplify, the important pieces of information. So a key concept doesn't just pass through the model once and disappear. Now, it gets held in the state of resonance. This creates an active, persistent working memory, just like the one in our brains.
And for the long-term stuff, for stability, we have what's called attractor memory. You can picture this as creating stable grooves or little valleys in the AI's landscape of ideas. As the AI is thinking, its state is naturally pulled down into one of these stable grooves, which represents a coherent thought. This is the anchor. This is what stops the model from just drifting off into nonsense. It gives the AI a stable concept it can always come back to, which should drastically cut down on hallucinations. So let's put all the pieces together and see how this thing would actually work. First, some input comes in and it gets turned into those really rich spinor embeddings, our concepts that have both direction and rhythm. Then that information flows through the resonant blocks, which keep it vibrating and active. The attractor memory module makes sure the main ideas stay stable and don't get lost. And then there's this really crucial part, a temporal workspace. This gives the model a place to loop, to actually mull things over and evolve its state before it gives you an answer.
So what's the big payoff for all this complexity? I mean, what's the point? The goal isn't just to build a different kind of AI, it's to build a fundamentally smarter one. And to do it in a way that doesn't just mean throwing more and more data and energy at the problem. The benefits they're expecting are, well, they're game changers. We're talking about real long-term memory, not just a tiny little context window. We're talking about a massive drop in hallucinations because the AI's thoughts are anchored to stable concepts. The ability to do a real chain of thought, not just imitate the pattern of one. And maybe the wildest of all, the potential for the system to have a model of itself. Oh, and here's the kicker. Because it's designed to be efficient, kind of like our brains, it's supposed to run on the GPUs we already have today.
This quote just perfectly sums up the entire philosophy here. For the last few years, the big AI race has all been about scale. Who can build the biggest model? Who can train it on the most data? SRGI basically argues that's not the answer. The way forward isn't about being bigger, it's about having a better, more fundamentally sound structure. A structure that's inspired by physics and by our own brains.
Now this all sounds pretty amazing, right? But is it just some pie-in-the-sky theory? The proposal says absolutely not. It actually lays out a clear, practical roadmap to build this thing.
And what's really wild is how concrete the plan is. This isn't some decade-long research project. It's a 10-week roadmap. Weeks 1 and 2, develop the spinor embeddings. Weeks 2 to 4, build a prototype of the resonant transformer. Then you integrate the memory, train a baseline model, and by week 10, you're running cognitive tests and releasing a paper. It's an incredibly aggressive, focused plan to prove, piece by piece, that this can actually work. And that brings us right back to the central mission. This is the ultimate goal: to completely shift a paradigm away from models that are just predicting the next character in a sentence to systems that can maintain a state, that can reason, and that can actually think. Which of course leaves us with one last, really provocative question. This proposal lays out a possible way to get there, but it really makes you wonder, if we actually pull this off, what happens then? What does a world look like when our machines finally, truly start to think?